A good fighting game requires a lot of programming finesse while playing offline with bots, but the same goes while playing online against other players. Every millisecond counts when you're aspiring to be the best. Talking about the tech side of multiplayer will be our second speaker, Peter Adamondy, the founder, programmer, and game designer of the Slovak company Triple Hill Interactive that is currently developing the one-hit kill fighting game Die by the Blade. And we are very happy to have Peter with us today, since he's from Košice, the place where the recording and the online edition of Game Days is coming from. So I would like to welcome Peter on stage. Peter, hi.
Hi, Miloš. Thank you very much.
The stage is yours.
Thank you. Hi, everyone. My name is Peter. I am a studio head of Triple Hill Interactive. I'm also a programmer. And today I would like to show you basically how we approach the multiplayer in our one-hit kill fighting game Die by the Blade. It's not going to be deep technical talk. It's more of a general, basically, approach that we chose. And I will show you also some methods that are widely used by industry professionals or industry games today, and how we kind of use that information to create our own system, and actually why we didn't use all their methods that they use in our game. So let's start. So first question is why networking is so complicated in the fighting games. So the main issue with the fighting games is that they rely on frame data, and basically every single action is linked to the animation data. In shooter games, for example, PUBG or any kind of shooting game, but Battlefield as well, and so on. So these games can use many tricks, like networking interpolation. You don't need to be extremely precise. There are two basic options that you have. So when you calculate the damage, when you fire a weapon, there is a raycast through the world, and if you hit something, basically you can give it a damage. That can happen on the client, and then basically client just says, okay, so I hit this guy, kill it, and this is sent to the server. And the server basically replicates that information across the board. This is fine, but it has some disadvantages, especially it's really easy to cheat. But it's understandable why they do it. For example, if you have so many players shooting all at once, if the server would do the check, it would mean basically congestion of traffic, and the server would be really slowed down for everybody playing, even the people who don't see actually shooting somebody. The second approach obviously is for smaller games. Usually this the Counter-Strike is a good example of that, where hits are calculated on server. So basically client says, okay, I want to shoot from here to there, what did I hit, right? So server calculates that and sends the information if somebody was hit. The downside of that, you have situations where you think that you hit somebody, but actually server disagrees about positions of you or your target, and basically you will see headshot, and you can actually see blood splash or something like that, because the effects are calculated on client, but have an issue of actually not hitting anybody because he was somewhere else, because server didn't have you didn't have that correct position of your opponent. In fighting games, in shooting games, that's fine, relatively fine. People don't like it, but it's manageable and it's understandable. In fighting games, this is a big issue because since it's a frame-locked simulation, basically you have few frames that you can actually execute some action, and if you are in disagreement with the server or other clients, basically all three of you will have a different view of the world, which will diverge over time. So the common approach, which is replication, is just not going to cut it. So there are basically three main ways to do multiplayer. This is a small table that shows you kind of like comparison between three main methods. So the replication, which is a standard way to do it, like shooting games use it, and many other games, and it works fine there. For fighting game, this is not so robust. You need a lot of data because if you sending all the desync information all the time between clients and the server, basically that can lead to a lot of data, and a lot of data transfer will basically have an impact on your latency, so it's not ideal. Good step forward was with the lockstep. It was initially, I think, used for strategy games. What it means that basically all clients are simulating sort of in a sync, and they cannot move without the input or basically without agreement on what should happen. This is awesome. It means that basically server, client, and the other client, or you, you always see the same thing over time. The problem with that is obviously what you do is you actually send the input and says, okay, it will be executed later down the line, and basically allow the packets to travel over the network. And when that packet arrives, basically they say, okay, so we will execute this action that you send us later in, for example, 2 or 3 frames. This gives some latency. It's not big deal in fighting games. It's commonly used. The question is how much, like the time buffer should you have? Like the best case is that you use lowest possible, so you don't feel the latency. The worst case, for players, and but best case for your network is if you use high latency. So you give a lot of time for packets to travel. If some packet doesn't, arrive, it will be then resend again and so on. So you give your systems a bit of a leeway. You give it a bit of space to work. The best approach that we have currently is a rollback. So rollback is the system very similar to lockstep, or it's extension of the lockstep. It's basically something that you have to implement first. And what you do is when you receive information, and all the clients and the server just simulate reality on their own place, on their own systems. And when you receive some correction, like 5 frames before, this guy actually hit the button. So what you do is you actually stop the execution, you go back in time, apply that action, and then resimulate it back into the future. And all the system has to support that. This is obviously really hard, but it's much harder to implement than lockstep or replication. But it's really robust. It doesn't robust. It doesn't need a lot of data because what you're sending is actually just inputs. It's extremely responsive because basically what you see is always the same kind of frame. And when you hit the correction frame, you just resimulate. So it always looks the same everywhere on every place of the world. So this is the best thing that we have. The latency is basically 1 frame. That's it. There's nothing better. So you would say, okay, so why are you not using, well, you should all use rollback, right? Yes, and people are actually saying that out loud on the internet. Obviously, I do understand why. But the problem with rollback is that it actually requires a massive amount of work. So the first thing that you really need is determinism, which I will talk a bit later about. Then the second big thing that you actually need is all the system should be able to store their state. You should be able to rewind all the state of the relevant systems and then roll it forward into the future and do that in a 1 frame, because otherwise there is another frame and this will just scramble data. So you just need to do it in 1 single frame. So you have in 60 FPS games you have like 16 milliseconds to do that. And that's it, which can be quite expensive to do. And, well, it's really hard to implement on the systems that are not deterministic, that doesn't have lockstep. to have all those systems work properly. Obviously, you also need your networking layer to work in a special way to allow you that, and yeah, otherwise it's just a big mess to implement. It's really hard work. So as you can see, NetherRealm Studios, they have actually talked about the implementation of rollback networking on YouTube. You can watch it. It's from GDC, I think, 2015. There was a lead programmer. His name was Stallone, I think, very similar to the actor. And what he said was basically that 4 to 12 concurrent engineers worked for 9 months to implement, which means 7 to 8 man-years of work. And they already had a deterministic simulation in place. So that means it's not going to be possible with our team. We're just 6 guys, 2 programmers, me, half of a programmer, and basically the artists and animators. This is just not going to work. We will, never finish a game like that. So we needed to find a better solution, or some kind of solution that would work for us, that would, do the determinism, do the lockstep, but to not really rewrite the whole Unreal Engine, because game is on Unreal Engine, and we just want to rewrite the whole engine. We did end up rewriting some parts of the engine, but it was much less substantial than if we would decide to go full rollback. Maybe in the future, So I was talking about determinism. Determinism is basically a philosophy. It's best described by the mechanical universe. So the idea is that if we would know every position of every particle at one specific moment of whole universe, we would need massive computer, bigger actually than the universe. But if we did, we would be able to predict future infinitely into the thousands, millions of years to the future. We know that that's not actually possible, not just because we don't have a computer bigger than the universe, but also that there is a Heisenberg uncertainty principle. So you are not actually able to measure particles in this way. But anyway, the idea is good, because what it says, simply put, is that if you have a system and you use the same inputs to it, you should always get the same outputs. So, whatever the machine is, we can call it deterministic. So whatever rules are in there, you don't really care, as long as the same input produces the same output. So this is basically a requirement of both lockstep and rollback. You can do both without it, but you will have a lot of these things. This is actually what we kind of end up doing. The main issue with the computers and determinism currently is basically floating point math. The calculations on floating points numbers diverge, and they are different. It can be different. It will be the same on the same computer, the same CPU, but if you, like, for example, take Intel or AMD and you run the calculation of some irrational number or some like big number with many floating point, many numbers behind the floating point, you can have different values, and these differences are really small for normal life. We don't really notice them because they are concatenated, they're removed from the actual calculations, they're rounded up, but over time they will add up slowly, and if you do them in every single frame, these differences will cause a divergence in reality. So what you actually do is you're using the integer or whole number math. So you cannot actually use, you can maybe, but it will be much harder to sanitize your code to have all the numbers properly calculated on all the systems all the time. The great about this idea is that normally if you have a game and you are syncing all the positions, all the stuff that's happening in the world, you need a lot of data actually to transfer between clients and servers. And imagine the world like Battlefield, where you have 50 players, and you need to transfer the data from 50 players to the server, and then back to from each and every single of the 50 players. You need to do that. It's a lot of data, a lot of stuff. There are methods. You can compress your data. You can just send if something changes. You can send just one value from the vector and so on. But still, it's going to be quite large. So if you have a deterministic system, you don't need to do that. What you need to do is just transfer the inputs. And if you transfer the inputs, the system, if it is deterministic, will produce the same output. So that means the simulation will run in the same way everywhere, and you just transfer simple clicks, and yeah, I did that, I did, I moved, and so on and so forth. So it's much less required for networking systems. You need much less data, and it's very smart. Basically, this was used for I think the Age of Empires, the strategy game, because they had this problem of having lots of units, and they would need to synchronize their position and stuff like that. So they ended up doing the deterministic simulation of those units, and basically just transfers inputs, and it ran really well on all the systems. At that time, the internet connection was somewhat slow comparing to this day. So that was another, thing that they kind of need to hit because they had the transfer ceiling. All right, so what we did, actually, well, we couldn't do rollback, we couldn't do lockstep, so we did both, and also some bit of replication. So idea of that is, okay, we cannot have a rollback, but we can use some of the principles of that. We can like stop execution, go back and do something else. We cannot have a lockstep, like per se, for every single frame, but what we can do is at least synchronize those actions and say, okay, so each and every action will be the same on all the clients and server as long as they have enough frames, as long as they have enough computational power, they will be the same or almost the same. And if they are not, we can use replication to fix those errors. So for example, we have a movement, our characters moves, and use root motion, which is the information from the animation that moves the capsule or move the character around. Obviously, that's fine, but what you need to do is basically move all the characters on the same systems at the same time. So we ended up using input delay. I will talk about it a bit in a minute. Basically, we are compensating for the round-trip time of the packet. The clients and the server needs to synchronize their clock, so they agree on what's the actual game time. You can say the frame, or just float number. Okay, this is time is 12. Everybody agrees. It's not like, oh, my time is actually 12.00.001. No, it's just exactly the same, or almost exactly the same. The differences are, very, very small, like negligible. Then each client basically can, simulate his own world, all the attacks, detection, collision detection, everything, effects, damages, stamina loss, and all those things, and basically then sees what, okay, so the server thinks that you did that because everybody should do this at the same time, so only the differences are fixed. Basically, this only happens when there is a disagreement between client and server, and I will show you how we kind of resolved the disagreement between those. So the first thing that we did was input delay. The idea behind it is to suppress the round trip time of the packet. So basically, when player presses the button, what we do, we wait for, we just send the information to everybody and wait. And since our clocks between client 1, client 2, and the server are completely synchronized, we can see how the packet travels. So what you see on the arrow, there are white arrows. So client 1 sends the information. I will execute, for example, an attack in about 8 frames. This travels to the server, arrives to the server at frame number 3, and the server uses that frame to, put the action into the action queue. So basically they say, okay, I'm going to execute that at that same frame that you are going to do. And since your travel time was 3 frames, I will subtract those and set the action in the future. Sends that information to the client, another client. This travels longer, for example, 4 frames, arrives at the 6th frame, and the client who says, okay, I received it, I see the dilation between you and me, so I can, safely, basically, subtract 6 frames and basically queue the action. So when the frame 8 comes on every single client and server, the action is executed simultaneously everywhere. This works really well. Basically, if you think about the frames, you can think about 8 frames at 30 FPS, because that's animation frames, it's not the game frame. And this should cover basically 80%, 85% of all the traffic demands. Usually, the dilation between actually client 1 and client 2 isn't as big. This is like really bad scenario. Usually, it's just few frames, 3, maybe 4 frames, and that's it. From the data that we were researching about the people's connections to the games, we know that a lot of people are having around 50 of latency time, so travel time from the server to client and back, of course. And more than 90% have less than 80, 85. Our system allows, with using that, the input delay can allow around 133. I will show that later. So the problem with this approach is obviously the situation where you have an action that should be executed at frame 8, but the travel time is longer than those frames. So what we do then? So what we do is simply what kind of like Rollback did. So each client executed some action, can execute some action at frame 8 that differs actually from client 1, right? What we do is stop it. We rewind the animation and start proper action, and then rewind it forward. Like say, we have animation, we know, okay, so we are behind 1, 2, 3 frames. We can take that time and actually move the animation forward. That obviously means that when the attack plays, you will lose on client 2, you will lose some frames, you will lose some time. What we did, or what we are doing, is basically the game design has to take that into account, and we have the time frame for that. I'm sorry. This problem. What we're actually doing is that we don't really jumping in frames. We are lerping or moving it fast forward. This required some tinkering with Unreal Engine, but it works really well, surprisingly. And basically, what it is very simple kind of rollback, if you would say. It's not really a rollback because we are not able to take back, for example, the particles that were spawned. So if you saw some sparks, like when weapons get hit, they will be there. They will stay there. We try to remove it. Say, okay, so this particle system shouldn't be spawned really, because there is some difference. Because this action actually didn't happen or happened in a different time. But what it led to was we're actually noticing more the delay than if we just leave it there, because people see the sparks coming from the blade. They can associate some action with it. But if you see the sparks stopping in the mid-flight and then disappearing, that's much more intrusive than anything else, than actually jumping in animation or other things. Then the second part was, to have deterministic rules. So instead of having a massive code that would say, okay, so if this, then that, and if not that, then this, and so on. So had like this really mess of a code. We decide, okay, so we don't want to do that because it's hard to maintain. You don't really see what's really happening if it's really big and you have a lot of variables coming and working together, and you have a lot of stuff to replicate then, and it's really just really big mess. So idea was like, let's make it simple and say, okay, so we have rules. And what we need, again, is this machine, right? So we just say, okay, so if, like, for example, hit happens, like I slash, my character slashes the enemy, and, hits his head or arm. So what should happen? So what we do is we stop everything. We look at the state of the attacker. We look at the state of the guy who is, receiving the damage. And basically from their information, we kind of subtract the first part of the table. These are like the states. So we extract the information that we need to decide what should happen, and then we have a table that says, okay, so if this row happens, then this will happen with the attacker and with the defender. So you can see that there is, okay, so if there is attack 1 and there is no defense action, the defender will be staggered and there will be damage applied. Right, defense result state is stun. So we will play stagger animation. He will receive stun, which is state where he cannot do anything really. So it's a penalty of not doing anything. And then we will apply damage, right? We don't say how much. We don't say, oh, play this animation at this point. We are just saying, okay, so this should happen. This, results were then translated to animations and action in a game, which describe like stun state, starts timer, and stuff like that. But it's not rules like if this then that. It's just you're trying to find the row of the table that describes the situation that we are currently in. This is completely deterministic. Everybody has the same table. Everybody has the same rules. We can change them on the fly. We can change them with different tables. We can modify them. This is really good for testing because basically we can change the rules in the table and then test it out how it works. It's really speed up the development. So this is like part of the deterministic simulation that we do. The whole decision wouldn't be possible or wouldn't be correct if we did it on one character or another character, and they would jump around and basically exchange the data. So what we're actually doing is we have an object that watches those characters, listens to their events, their states, watches their actions, which are replicated using or executed using the input delay and lockstep. And then from that information, he uses the table to decide, okay, so you actually hit the guy. It was an arm. He wasn't defending. He wasn't using a parry. So let me look at the table. Okay, this guy has a stun. This guy is okay. No change required. And this is what the referee does all the time. The good thing about it, or nice thing about it, is we actually can easily change rules. We have one place where all the rules are calculated, the effects and animations, all the things are made in one place. And it's really nice because we can turn it off and turn it on as we go, as we want. So for example, you have a fight and referee is there only for when the timer starts, like go, when you have like 3, 2, 1 and go. We don't have a 3, 2, 1, but we have a go. And basically only during that allowed time period where damage is calculated, he actually does his thing. So it does the decisions. If something broke and you actually have an input or you want to hack the game, and you are trying to do the damage sooner than in allowed time, it's not possible. You are not going to do that because that's the referee's job, and he's not active at the time. And since we don't like easy solutions, we wanted to do the tournament mode. We actually didn't want, but a lot of people actually asked for it. And we were thinking, okay, so we can do that. The idea is, in a tournament mode, you can be local, it can be online. What you do is you actually connect with, for example, 8 people. The game decides, okay, so you guys play together, They basically assign the matches to the players, and then matches start, and they are concurrently running at the same place, in the same room, I would say, on the same server instance. You always occupy the same server instance, so we can actually watch what you are doing. We can collect the data. Okay, so you hit his, pelvis or his arm 2 times, so he should be dead. We can count who won. We can change the rules of the game, like say, okay, so we have 5 lives instead of 3 lives, and it will apply to everybody. So we needed to do some. The problem with that is that since they are existing in the same space, what happens is that you would be able to see all the 8 players at the same time, and they will just hitting each other, and that would be just completely crazy, right? So we needed to isolate the tuples of the players into like virtual arena. The referee is actually attached to it. So again, this, you can think about this object, which is like small world within the world. It's like Inception, like you have a game and you have arena, and you have a smaller, smaller world that simulates all those things for you. This is a great way because we can actually, in a single player, we can replicate the same rules, same things, and we just spawn the arena, say, okay, we want this guy fighting this guy, here's the input, go on. Here's the referee, here are the rules. And it works really, really lovely. Basically the game, then the arena, when it's like finished, it just completely cleans itself up. So that's also a really nice thing. The last and big part is network architecture. So, as I said in an earlier slide, one of the problems of input latency or lockstep system is, or their combination of, is that what you do is actually you need high input latency to cover cases where you have high latency in packets, right? So idea is, okay, we want as low latency for the fighting game players so that they don't feel it as much, but that requires us also like decreasing amount of time the packets has to travel between servers and the clients. The common solutions right now is basically you have a cloud server that runs instances, everybody connects it. The massive servers in Frankfurt, in Hong Kong, and in Tokyo, and Melbourne, and in various places in the US as well. And basically you can say, okay, so I'm going to play on European server, and if you are from Oslo, you are connecting to Frankfurt. If you are from Italy, you're connecting to Frankfurt. If you are from London, you're connecting to Frankfurt again. This leads to the travel problem. So basically, if you are from Frankfurt, you will have much better connection to that server. You will have much less travel time, so you will be kind of in advantage. The other guy who is from Oslo and you are playing with him, well, not so much. So what's the idea? The idea was to, okay, so we don't want one massive server. Let's have hundreds of them all around the world. To be precise, more than 150 servers are running around the planet at this moment, playing online games with distributed systems. Basically, we're working with a company named called EdgeGap. You can look it up. They are using containerization technology for that. What it means is basically that you can have very small, very not really demanding servers all around the planet. You just send the information, okay, so start with this server. It has all the operating system, it's already started, it's booted up, it has all the RAM in it, and you just spawn it, take a few seconds for virtual machine to run up, to spool up, and yeah, servers is running and waiting. So players can connect, play on that server. And what's really nice about it is that the algorithm, the matchmaking algorithm, is using proximity, so distances, and it's trying to find the best server for you. So, for example, if you are in vicinity, like, for example, we are in Košice, and I want to play with somebody, and the only available player is in Prešov, which is 30 kilometers away. Hopefully, we can find some server that is close, is in the same distance to both of us, so that we both have the same kind of distance to the server, which equalize the playing field. There are other solutions like Google Agonis, Azure Sys, and PlayFab, but they are not really there yet, I guess. We decided with EdgeGap so far pretty happy. We measured the average, the best response time that we had was like 20 or 15 milliseconds. The usual that we have, and we have a test server for worst case scenario in Frankfurt actually. That was actually around 30 milliseconds, so it's quite good. All right, and conclusion. Yeah, there are downsides. We are not as good in solving the RTT problem. It's about half. We have been able to combine lockstep replication and kernel rollback in our system in a very specific way, but still uses delay, still has some latency. It's not like massive, but it's still there. The grade would be to not have it at all, but that would require just full rollback implementation. And obviously, we need to fix the sync errors still. So that's unfortunate, but reality of the system. So thank you very much for listening. If you have any questions, please hit me up. And we are actually hiring, so if you want to work for us or with us, that'll be awesome. Just hit me up at developer@triplehill.com. Don't know if you see the address because the background is same color for some reason as the text, so I'm sorry. Anyway, look at the triplehill.com jobs. Thank you very much.
Thank you very much, Peter, for a very fascinating, hardcore technically oriented lecture. I myself am not a very technical person, so I guess I will start by reading some questions from Slido.
Yeah.
One of the first one is, what are the biggest challenges when designing single-player and multiplayer fighting game, in your opinion?
Well, there is no really single player, like if we talk about single player exclusive, it's much easier because what you need to do, you don't really need to think about how the AI is feeling about the fight, if it's fair. So easier for you to do. You can have this power fantasy. If we talk about local multiplayer, or online multiplayers in general, well, you have to think about that. You have to think about, okay, so is it fair? What can you actually do when some other players? Because it will feel great to have like other guy just smash the bits very easily, right? But how he would feel about it, it wouldn't be really great. So what you need to think is counterplay much more than just some kind of adventure single player experience.
Mm-hmm. Okay, another question is, are there any risks of using cheats or exploits by the players during matches with your system, and are you addressing it somehow already during the development?
Right, so, well, you cannot really prevent cheats, yeah, right? It's not possible. What you can actually do is, and what we have is, have a simulation on the server and then basically send the information to the clients. And we can detect the discrepancies between client and server. So if somebody's trying to do something which is not okay, or a game doesn't expect, we can detect it and kick out the player. That's it. The problem is that the techniques that cheaters can use, like for example in the memory tinkering, they open the game and then look at the memory and change the values and see what's happening. This is not preventable. The only thing that we can actually do is check with the server. Mm-hmm. We always think about the clients as compromised. We think about the Steam client as compromised. We think about the game client as compromised, as someone hacked. So if you go into that with that mindset, you will, automatically like add or, change your solution to accommodate it.
Right. I think you already addressed this question a little bit, but maybe let's try getting a bit more into detail. Can you reveal what alternatives you were considering and why did you choose yours? What are the criteria to pick the right solution provider? And fingers crossed.
Thank you very much. Well, we tried the Amazon AVS. It was fine. So there are some issues with the AVS as it's really built for massive companies. So it requires it basically requires integration engineer, right? You have a lot of variables, a lot of stuff to, set up, and it's really painful. Also, since basically everybody is using it, the uploading time to AVS and running the server instance, which is actually a computer that also runs a server of the game or the instance of the game, it took about 1.5 hours. With EdgeGap, we have that in 15 minutes. So we build the game server, upload it there, bang, it's just going, right? What we do is just create the server build, like we are using Linux file, so it's not server.exe, but we just pack it up with the operating system in a nice package, just send it there, and just completely going to be distributed all around the world. So it's really easy for us to work with them. So easy of use and the flexibility that we have with them.
Are you also considering the possibility of providing dedicated servers for the players to set up their own rules?
Right. So this is the question more for our publisher, if he allows that. It's more of a business decision. I'm not sure. Like we can do that technically. The main problem would be to have how to set the game so that it actually receives. So what we decided kind of at this time is that we have a LAN. So you can play on LAN. Mm-hmm. There is no internet connection required. You can play with your friends. You can have LAN parties without internet in some cabin in the woods. It's fine. It's going to work.
Right.
And you can create on the LAN tournaments as well in the game. So it will work in the same principle like proper online matchmaking game.
All right. So, and last but not least, maybe tell us a bit about how the development is progressing and maybe when we can expect some big news or some ETA.
Right. So game
future.
has to go out next year. This is my personal goal and of course publisher's goal as well. We're currently doing testing. So basically you take the people, put them in the room and just give them games to play and watch what they do. And we're now fixing or stabilizing the gameplay. So we have a lot of values that we can change, like for example, how much stamina you would use for some kind of attack, or maybe timing of an attack is too low, like you can spam it and so on. So we need to balance the game. This requires a lot of iterations. We're also working on characters. We have a character customization in game. We have a weapon customization, so you'll be able to customize your weapon, as you wish. So there is a lot of assets. We're also working on single player, which requires a massive amount of assets. There is a story. We have a challenge mode. We have a tutorial. We have a lot of modes. So we are working on that. We want to replay system to work as well. So recording the matches, you can see them then, or upload them. It's not going to be video. It's going to be in the game, but you can re-record them. So if you play and have some nice situation that you want to share, it will be there recorded for you, and you can restart and play, pause, rotate camera, fly around the arena. So there is a lot of features that we want to cram into the game as much as possible. So this requires a lot of time, but we're on a good track. The systems work. Finally, the multiplayer was working as well. It was a lot of work. It just took us 2 years to implement this. Mm-hmm. But it's finally working, and we're currently, cleaning the gameplay and balancing and recording a lot of animations. Some animations work, so we can, we had to throw them out add new ones, and so on and so forth.
All right. So still a lot of work to be done, but hopefully we can look forward into 2022.
Yes,
to finally
yeah,
play the
definitely. Even if the game is not going to be 100% great, but I feel like I am kind of guy that it will not really happen in my lifetime. That I would be like, yeah, it's 100%. I can, you know.
So
It's
personally, I'm looking forward to it very much. Thank you very much, Peter,
Thanks.
for your lecture. And we are slowly nearing the lunch break. And with this in mind, I would like to remind you to check out our website schedule for the discount codes on the food service delivery Food Panda, which is one of our main partners for this year's game days. And see you after the lunch.